Hello everyone and welcome back to my channel. By now, you're already familiar with the power and elegance of eigenvalues and eigenvectors. You have journeyed with us through finding them, tackled repeated eigenvalues, and even wielded the mighty Cayley-Hamilton theorem to find powers, polynomials, and inverses of matrices. Today, we are taking our understanding a step further by exploring the nuances of algebraic and geometric multiplicity of these eigenvalues. These concepts provide deeper insights into the behavior of our matrices and their corresponding linear transformations. We'll be using familiar 2x2 examples to illustrate these ideas. So let's dive right in and unlock another layer of linear algebra mastery. As a quick refresher, recall that for a square matrix A, an eigenvalue lambda satisfies AV is equal to lambda V for some non-zero eigenvector V. Eigenvalues tell us how vectors are scaled by the linear transformation represented by A. Today, we are focusing on the idea of multiplicity. Let's start with algebraic multiplicity. This is simply the number of times a particular eigenvalue appears as a root of the characteristic polynomial. Remember how we found those crucial eigenvalues? By solving the characteristic equation, determinant of A minus lambda I equals 0. This gives us a polynomial in lambda, and the algebraic multiplicity of an eigenvalue is just how many times that specific value of lambda makes this polynomial equal to 0. Let's revisit a simple case with the matrix. The characteristic polynomial of this matrix A is determinant of A minus lambda I equals 0, and you can solve it and reach out to the conclusion that the characteristic polynomial is 3 minus lambda 1 minus lambda equals 0. Therefore, the roots are lambda 1 is equal to 3 and lambda 2 is equal to 1. Since each root appears only 1, so the algebraic multiplicity is 1. That means that the algebraic multiplicity of lambda 1 is equal to 1 and algebraic multiplicity of lambda 2 is equal to 1. Now for something a bit more interesting, consider the following matrix. The characteristic polynomial of this particular matrix turns out to be 2 minus lambda whole square is equal to 0. Here, the eigenvalue is 2, which is a repeated root. It appears twice in our factored polynomial. Therefore, the algebraic multiplicity of this particular eigenvalue is 2. Next up is geometric multiplicity. This refers to the dimension of the eigenspace associated with a particular eigenvalue. Remember, the eigenspace of lambda, E of lambda, is the set of all vectors V that satisfy the equation A minus lambda times I into V is equal to 0, along with the 0 vector. Essentially, it is the number of linearly independent eigenvectors we can find for that value. Now, let's go back to a matrix B for which we have got the algebraic multiplicity of lambda equal to 2 as 2. Let us find the eigenvectors of B for lambda equal to 2. For this, we will be starting with solving A minus 2 times I times V is equal to 0. Substituting for A, we get 2 minus 2, 1, 0 and 2 minus 2 times V, call it as x1, x2 is equal to 0, 0. We have here 0, 1, 0, 0 times x1, x2 is equal to 0, 0. Since the second row is a 0 row, this reduces to 0x1 plus 1x2 is equal to 0, giving us x2 is equal to 0. Thus we have the eigenvector to be V is equal to x1 and x2 is 0, where x1 is any real number. We can only find one linearly independent eigenvector, namely 1, 0 if we put x1 as 1. Thus, the dimension of the eigenspace for lambda equal to 2 is 1, and hence its geometric multiplicity is 1, and we can write here as the geometric multiplicity of lambda equal to 2 is equal to 1. A crucial point to remember is that the geometric multiplicity of an eigenvalue is always lesser than or equal to the algebraic multiplicity of the eigenvalue. In our example, we had got 1 as the geometric multiplicity and 2 as the algebraic multiplicity. Thus, we got that the geometric multiplicity is strictly lesser than the arithmetic multiplicity. If we have a matrix for which arithmetic multiplicity is equal to the geometric multiplicity, it has significant implications, particularly for diagonalization. Now it's your turn to put these concepts into practice. Consider this matrix C given by. Your challenge is to determine the characteristic polynomial, find all eigenvalues and their algebraic multiplicities, and for each eigenvalue, calculate the geometric multiplicity by finding the dimension of the eigenspace. Share your insights and solutions in the comment sections below. And there you have it, a deeper dive into the algebraic and geometric multiplicities of eigenvalues. Hopefully, this builds upon your existing knowledge and provides a more complete picture of matrix behavior. If you found this explanation helpful, please give it a thumbs up and subscribe for more advanced linear algebra explorations. Don't forget to hit that notification bell to stay updated. We are always striving to create content that's most beneficial to you. So in the comments below, please share any suggestions for future video topics. Are there specific areas of linear algebra or mathematics you would like us to tackle next? Your feedback is invaluable. Thanks for continuing your linear algebra journey with me. Keep those matrices multiplying and I'll catch you in the next video. Thanks for watching and happy learning.